acids and bases. So if I gave you this equation, I said, what are the products? We're in the acids and bases unit. What's the definition of an acid? A Bronsted-Lowry acid, I guess. Sorry. Donates a proton. What is the only thing capable of donating a proton in this?
Bicarbonate?
Yeah, H2CO3. So it's going to dump a proton. And we get that. That's all that can happen here. All right? What are the acids in this reaction? Bicarbonate. Oh, you mean this one?
No.
This one?
Yeah.
This is the acid for the reverse reaction, right? And so these two are bases because they're accepting. Okay. What happens if I take CO3 2 minus okay, what do I get? NHPO4, right? Minus 2. And the charges have to balance. So we have minus 3 on the left side, minus 3 on the right side. Okay. So we know what the acids are. The acids are this, and going back the other way, this. So here's my question. Which is the KEQ for this reaction greater than 1 or less than 1? And if you answer, you have to explain why. Well, you can. You just have to have an explanation. The forward or the reverse? That's all I'm asking.
Is it less than 1 because the stronger acid's on the left?
So what you have to ask yourself is because we set up a battle between the two acids. Okay, we have this acid pushing this way, this acid pushing back this way. So you have to ask yourself which acid is stronger. Okay, so then you go to your data booklet. What do we got? H2PO4 minus, and hardest part about the data booklet is finding everything. H2PO4, there it is. Oh, I think H2PO4 and HCO3. Where's HCO3? There it is right there. All right. There they are right there. Okay. H2PO4, HCO3. Which is the stronger acid? The one that's higher up on the table because it has a lower Ka. Higher Ka, sorry. Larger Ka. That's a better way to say it. And if you look over here, it even says, little arrow, strength of acid going up. So the one that's higher on the table has a bigger Ka. That wins the battle. So, where'd my notes go? So, since is stronger than the products are favored, and KEQ is greater than 1. Does that make sense? Okay. Well, I'm going to say KEQ because it's a reaction now. We're looking at the different Kas of each acid. Okay. And KEQ is Ka, right? Essentially.
Because it's it's a stronger acid, it'll create more ions, so it'll push to the right.
Well, it's this wants to protonate this, right? But this wants to put a hydrogen onto here, okay? And if it does that, it pushes back this way. This is pushing this way. So they're competing against each other. Which one is a stronger acid? This is the dominant acid. So it wins the battle and the equilibrium gets pushed this way. Does that make sense?
Yeah.
That's all we're doing. Okay? That's the theory, the theoretical behind it. There is a mathematical. Would we like to look at the mathematical? Too bad. All right. So the mathematical. Now, I'm not going to ask you to reproduce the mathematical. I'm not even going to go into the proof of the mathematical. If you want to see the proof of the mathematical, you can come up here because I have it written down. I know. Calm down. Okay? This is the mathematical. The KEQ, I'm just going to give you the formula, is the Ka. It's up to you. I won't ask you to reproduce this, but of the reactant acid divided by the Ka of the product acid. I know it seems backwards. Okay, if you come look at the proof, it'll make sense. I'm not asking you to use this. I'm not asking you to memorize this. I'm just showing you there's a mathematical theory behind this. Okay, so this is the formula. So if we look at the one we just did, the reactant acid is that H2PO4, right? What's the Ka of H2PO4? So if I go Ka of H2PO4 minus, is going to be 6.2 times 10 to the minus 8 divided by the Ka of the product acid. This is the product acid, HCO3 minus, which if you look on your table has a Ka of 5.6 times 10 to the minus 11. And if you divide those, you get 1.1 times 10 to the 3, which is 1,100, right? It's bigger than 1. That's all. Is it? Right? That's all that matters. Sorry, I'll move it up. Okay? So if you divide those Kas, you get this number. All we care about is that it's bigger than 1, which means products are favored, right? Because KEQ is that formula, which equals concentration of the products over the concentration of the reactants, right? I know this seems weird because we got reactants up top and products on the bottom, but we're looking at Kas in that case. And if you look at the math, it makes sense. Okay? Just I know you want to see the math. I will show you the math. Okay? So that's the math behind it. You don't need. I'm not going to ask you to do that. What I will ask you to do is, here's your reaction. Tell me what the products are. Tell me is the equilibrium bigger than 1 or less than 1, i.e., are the products or the reactants favored? Which is the stronger acid? That's all I'm going to ask you to do. Okay? So I'm going to give you one more question and then a couple of practice ones, and then we'll just move on to KBs today. All right. HS minus. Okay. You got to tell me what are the products and what are the reactants. But this one's a trick. Why is this what are the products? You know what the reactants are.
Because they both have hydrogen.
Yes. They both have hydrogen. They can both donate a proton because they both have protons, and they can both accept a proton because they're negatively charged. So which one is the acid? Which one is the base? What do? You look at your table and you determine which one is strongest. And then you can get the products. And then when you have the products, you have to look at them, the acid on this side and the acid on this side. Which one is stronger? Go. So what's the stronger acid between HS and HCO3 minus?
I'm guessing by not by.
HS and HCO3 minus. Let's find them.
H2S?
Nope. HS minus should be on there. Is it not on there? Is it not on?
So H2S is, but HS is not.
Ah. Okay, I'll just tell you. HS is not on our table. Well, that backfired. All right, I'll just tell you what it is. It is HCO3 minus is the stronger. So we get
So it becomes H2S.
okay. So now you can tell me. So that's this HCO3 is stronger than HS minus. So which two acids are now battling to push the equilibrium left and right? H2S and HCO3.
Oh wait, why? Yeah, I can't get why HCO is stronger. Why is that?
Because it donates the proton then, right?
It's like stronger means one kinetic proton more.
So H2S is
Supposed to
stronger.
know that?
You look on your HS minus isn't on your table, but normally I'd give you two on the table and then you could just look it up.
No, I mean like. And it explains to you why that is.
So
Because they both want to donate a proton, but why it's a stronger acid?
No, like why the stronger acid donates a proton over the weaker one.
why?
Because it forces the weaker one to act as a base. I don't know how to explain that other than
Does the same thing happen with bases? Like a stronger base will.
we'll rip a proton.
If you have two things that both take a proton, but one's stronger than the other.
It'll take the proton first. Okay, so which is the stronger acid between H2S and HCO3? So H2S is stronger than HCO3. Therefore, KEQ is less than what? Whoa.
Isn't it fair for the reactants?
Yeah, so it's less than 1. Because what's KEQ? Concentration of products over
I just
concentration
thought
of
it was
reactants.
reactants over. Sorry. But the reactants is bigger.
Okay, so then once you figure it out between these two, which is stronger, in this case it's this, these are your products, then it's a battle between H2S and HCO3. H2S is stronger than HCO3, so it pushes the equilibrium back this way, so you have more of this, so your KEQ is less than 1. That's what I will expect you to be able to do. Okay? Does that make sense? All right.